Okay, this first one here, does it take more heat to melt the ice or to vaporize the water? All right, so to vaporize, definitely more. And to calculate how much heat, since they're both 10 grams, it's 80 calories per gram to melt. 10 grams, so 800 calories, and 540 calories per gram, 10 grams. So 4,600. 4,600 is how many more calories it takes? Do you remember why we said that was the water took more to turn into a gas than to a liquid?
There's less air between the molecules. There's space.
No.
No, because it's breaking the bonds. Well, not. It's sort of loosening them up just to become a liquid, but to make it into a gas, it has to excite them a lot.
Keep going with what you said before, because you said loosen the bonds. I like that. So if I go from a solid to a liquid, I loosen the connections.
Structuralizes it, sort of. From ice, it loosens it and makes it fluid.
And then when I go from a liquid to a gas, what do I need to do?
Add more heat so it vibrates.
Yeah.
So you like shoot them off apart.
So now they're apart from each other. So when they're touching each other as a liquid or as a solid, they have a connection, a sort of bond. We're going to call it an intermolecular force later. But there's a connection there. So if I'm going from a solid to a liquid, I loosen the connection so they can move around. But when I go from a liquid to a gas, I have to completely break all of the connections. Because like you said, they just leave. They have to disconnect from each other. So initially, I'm loosening them, like Gideon said, and then I have to completely separate them out, like Eric said, when I turn them into a gas. So it takes more energy to fully break them apart from each other. Calculate the amount of heat needed to raise the temperature of 250 grams of water. Okay, so this one seems... Oh no, that's right. That was this problem that we were supposed to do, and I wasn't supposed to give it to you last time. Alrighty, so this is the problem that does this, right? And there are 5 parts to this. There's a raising of the solid, there's a melting, there's a raising of the liquid temperature, there's a boiling, and then there's a raising of the gas temperature. So on the angled portions, you use the equation that's Q equals mc delta T, because there's a change in temperature. And on the flat portion, since there isn't a change of temperature, we just use Q equals mc, and that would be this equation that we have up top right here. So 250 grams. So I'm going to Q equals 250 grams, and it's 0.5 calories per gram degrees C, and it's 52 degrees C. Okay, so the 250 that was given in the problem, where'd this 0.5 come from?
That is the specific temperature of ice.
Specific heat of ice, yep. And then the 52 degrees?
That's how many degrees you need to raise.
I need to get it up, add 52, or make it 52 degrees hotter to get myself up to 0 degrees. Okay, so let's see what we got here. $125, 52, 780 calories. Okay, now, so I guess we're going to talk about that in a sec. That's fine. 250 again, and then it's 80 calories per gram. And so calories, and then to melt, and then 250. Whoa, don't do that. 250 grams, 1 calorie per gram degrees C, and then 100 degrees C. So 25000 calories. And then we'll do Q equals 250, 540 calories per gram. I get 135,000 calories. And then the last one, sneak it in here, Q equals 250 grams, 0.5 calories per gram, degrees C. And then what are we taking at 28 degrees Celsius? 2 times 25. Oops. Cal. So, plus 135, plus 20, plus 780, plus 25. So I add all these up, 108,480 calories. Looks like 2 sig figs, so 180,000 calories. Wow, zero. There we go. What does the fact that the specific heat of water, liquid water, is 1 calorie per gram, and that the specific heat for ice and for steam is half of that? What's that telling you? To heat the ice or the steam that it is to heat the liquid. Okay. So we'll draw a heating curve. So we've got... Okay, so what's happening right here?
It is heat of the ice is
It's heating up to its melting temperature. What's happening though?
they're starting to fire.
They're just moving more, right? So what about this part right here?
Same thing.
And this part right here?
They're right.
All three of these parts are increasing they're increasing the speed at which the molecules are moving. What's not happening there?
They're not switching between phases.
Yeah, there's no phase change there. Okay, so then we can go here. And what's happening here? Well, that's a phase change. So the green parts, I'm using the energy to make the molecules move faster. And the red parts, I'm using the energy to do what? When I'm changing phases, what am I doing though?
Loosen or break bonds.
Yeah, loosening them or breaking them. So getting them to let go of each other. Alrighty. And this last one here. So when I'm finished with this, I need one N2O5, and then I need an O2, and I need an N2. All right, so there's O2 there, and there's N2 there. There's water. So is the first one okay? I can't quite tell, actually.
No, it's one now.
When I do these, what I do is make sure that the orientation of the three are correct. So let's do it like this. So I need a nitrogen on the reactant side, and there's a nitrogen on the reactant side, and there isn't any nitrogen anyplace else. So this equation has to stay right where it is. I need an oxygen on the reactant side, and I've got one here, and I've got one here. So one of those is probably going to have to switch. But I don't know that for sure yet. And then I need an N2O5 on the product side. And over here, I've got it on the reactant side. Okay, so that's a problem. So what I'm going to have to do with that middle equation?
I'm gonna have to swap it around, swap the sign.
I'll flip this around. I'll make that positive. All right, N2O O5 here, and then I'll write water here. And so then all of this stuff is gone. Okay, so I have the N2O5 where I want it. All right, so now that I don't want water molecules anywhere, right? And I also don't want hydrogen gas anywhere. So this hydrogen gas needs to cancel out, and the only way it can is with this one. And this water has to cancel out, and the only way it can cancel out is with that water right there. And this nitric acid needs to cancel out, and that's okay because they're on opposite sides of each other. So what I'm going to need to do is take that first equation and flip-flop it. So we will H2 plus 1/2 oxygen. And then we'll cancel all this stuff out. And right now I can go ahead and cancel out my water. I cannot cancel out my hydrogen or my nitrogen. So if I multiply this by 2, this whole thing by 2 here. Oops. So let's make this 2 times bigger. That turns into a 1. This turns into 3. This turns into a 1, and this turns into a 2, which is great because then I can get these 2 nitric acids to cancel out with those 2 nitric acids since they're on opposite sides of the arrow. And I can get this 1 hydrogen to cancel out with this 1 hydrogen. And that's a half of oxygen. This half of an oxygen. All right, something's wrong. What's wrong? What have we messed up? What have I messed up? Right now, if we balance this thing out, we have a I have that's what I want, and that's what I want, but I don't want this. So what do we do wrong with this? Because if I cancel out this half here, over here, then I have 2.5 oxygens, which I don't want 2.5 oxygens.
Because that's what I was trying to do at home, but that wasn't working out for me either.
Mm-hmm.
Because I didn't get a really good answer on this problem. I just
Two.
doing a lot of fiddling around.
Two.
And I even come here.
5?
Yeah, that's how I balanced it, but then I wasn't able to, I don't know.
Well, if I double this guy again, if I double this one again, that would be okay. It would handle that and that, but then that would mess up my nitric acids. If I double that, well, I'm going to need to double that. Okay, so let's try that. If I double this again, then this becomes a 2. This becomes 5. And this becomes 2. And this becomes 4. And so then if I double this guy, that becomes a 2. That becomes a 2. And this becomes a 4. And so then I can go ahead and cancel out these guys. So they cancel. And if I double you and you and you, that cancels one out, makes it a 4. And the water still cancel out. This seems wrong. Like I've got something wrong here. Yeah, this can't be balanced. Well, that sucks. You thought you did?
Thought you did?
Yeah, grab it. What did
I
I?
didn't. I was trying all this motion. It's not for me.
And 205 H2O. H2 plus a half of an oxygen. Multiply this one by 2, so that becomes a 1. This becomes 3. This becomes a 1. That becomes a 2. And then when I do that, then that cancels with that. That cancels with that. This cancels with this. I've got my 1 nitrogen. I've got my 1 N2O5. And I still have 2.5O2. And I cancel out that and that. It's technically half of what I need.
Like if you doubled everything, I don't know, like the balance equation you need 5 oxygens.
I think I just messed up a coefficient on one of these. That's got to be what it is. Like I think this was supposed to be a half. The oxygen down in the bottom was supposed to be a half, I think. No? Six halves is 3. Yeah, okay.